Hello everyone. Let us continue our further topic of the discrete mathematical structures. We were discussing the concept of the proposition, and we have solved some of the examples of that by considering some rows and columns. We have solved this one, and we have proved that it's a tautology. And we know what is tautology. Tautology is nothing but the resultant proposition should be in a resultant proposition. All the possibilities should be one, and the if you see contradiction in the resultant proposition, all the values will be false except that is zero. And a similar example is also there for you. In this, I'll just tell you how we can come to one conclusion, that is we are considering this as a we are considering this as a p and p conditional r. I mean, we are solving this, how this is being solved, and we are making a comparison between the last column with this one, and we'll see whether we come to a condition called as a tautology or not. Okay, and let me first tell you how we have drawn this tautology, um, by making use of propositions pq and pqr, and assigning x values, x y z values to p or q, p conditional r, q conditional r. And why these conventions are given? Just because we want this, we want p x and y and z. Okay, so because of that we have come across this kind of conventions of x, y and z. And since we have three propositions pqr, so we'll be having eight possibilities. And to be straightforward, p or q, how we have come across this column is p or q 0 0 0 0 0 0 0 1 1 0 1 1 1 0 1 1 0 also 1 1 1 1 and 1 1 1. So the important part to be stressed more here is, anyhow everybody will get the uh, uh, get done with the or operations and operations conditional one. And what is required here in this example is, we have two, we have this one, and we need to apply the condition among this column and the r column. Okay, that is, let me say this column as a p, and let me say this as a w and r. Okay, so this column 0 1 0 0, it will be 1. Why? Because in our condition we have only, we have only if our case is 1 0, then only it will be false, but in all other cases we come across the condition that is true itself. Okay, so 0 0 it will be 1, and 0 1 it is 1, and 0 0 again 1, and 1 1 it is 1, 0 0 1, 0 1 1, 0 0 again 1 1 1 1. So that's why it is proved that it is a tautology. So the ultimate aim in our example is, by using our truth table concept, we have to conclude that this conditional r is a tautology. So that's what we have come across in this truth table. Since all the elements or all these possibilities are one, with this we conclude that it is a tautology itself. So coming to the next concept, we are seeing the important part of our first module, that is laws of logic. So wherein you will have to remember certain laws. So there are basically 10 laws, and these 10 laws are to be remembered, and we come across these laws several times. And with this, with these laws, we are proving uh, many problems, and we are solving many problems, many examples we are deriving and we need to also focus more on these few other formulas also. In fact, these are not laws, but uh, we need to remember all this. But it is it can be proved by using a truth table, but we need not to worry about those truth table concept right now. But we need to remember, and some of what the properties like transitivity, substitution property, and we'll see some of the examples also once we complete the laws of logic. So this is what the laws of logic. The first one, it is very simple, the laws of negation, laws of double negation. Law of a double negation, or for any proposition, if you consider a p, double negation of p is nothing but it's an equivalent to p itself. Okay, so this is the first law. Double negation of p is p itself. Okay, equivalent to p. And idempotent is nothing but, if see any law, if you are considering, it should be operated for a or operation, and even it should be operated for the and operation. So that has to be taken care. And p or q, p or p, idempotent. So here both will be same, and when p or p, it is similar to, we come across a p itself. And p and p is also, that is p itself in the idempotent. But it will not be case, the same case is, if that all this is different, p and p, never it will be p. Okay, so idempotent means a same uh, variable you get, I mean the same proposition you get, if at all you come across p or p or p and p. So this law is called as a idempotent law. Identity, what is identity? Identity means whatever the proposition you are taking, the resultant will be the same. So when it will be same is p or f naught. What is this f naught? F naught is nothing but a contradiction. That is all the possibilities, if it is zero, then we come across the contradiction. P or contradiction will be always p itself. P and tautology will be always p. So this is an identity. Inverse law, suppose for any proposition p or inverse p, it is always p naught. P naught means it's a tautology, and p and p, p and p, so it is always a tautology. So whenever you come across an and, the possibility of contradiction will be more. And in case of the or operation, the possibility of tautology is more. So that thing you have to remember. Inverse p or inverse p is tautology. P and inverse p is a contradiction. I can say f naught. We denote it with a f naught. Commutative, it is just, or it is a domination. Sorry, p or t naught. If you perform an or operation with a tautology, then it will be a tautology itself. And if you perform an and operation with a contradiction, it will be a contradiction itself. So that is the conclusion what we derive from this domination laws for any proposition p. And for commutative law is just a swapping of those propositions. Swapping means p or q is equivalent to writing it as q or p. And similarly, p and q, it is, you can even write it as a q or p. The why this is in this manner, why this law is in this manner. Sometimes while solving the problem, so at that time we need to adjust in this manner. So that's why the commutative law will help you at that time. Okay? And this is the most important law, absorption law. What is this absorption law? P or p and p. P and p, p or q. So for any propositions p and q, p or p and q is equivalent to a p itself. Okay, so this is to be remembered. P or P and Q is equivalent to P itself, and P and P or Q is equivalent to P itself. Okay. If you perform a inside, if you are here, you are performing an AND operation, and you are performing an OR operation. But here you are performing an AND operation outside, and inside you are performing the OR operation between P and Q, and it is absorption law. De Morgan's law or De Morgan's theorem. Most important theorem or most important law where while solving a problem often you need these laws. So one of the most important is the De Morgan. Inverse of P or Q. Inverse of P or Q is inverse of P. The sign from OR is converted to and negation of P and negation of Q. So if you are coming to the AND section, inverse of P and Q is equivalent to inverse of P, or the sign is it is changed from AND to OR here, and inverse of Q. And in the last two, to consider in the last two, we have three propositions PQR. When you have three propositions, here also it is the combination of the propositions changes here. P or Q or R, here combining the first two and R remain same. Here the same thing, P and Q and R, first enclosing the brackets for the first two and R. Okay. Distribution law. Distribution law, suppose if we are coming across such a scenario like P and Q and R, first combining these two P or Q, and next performing an AND operation P or R. So first performing an OR operation with Q, and remains as it is, performing the OR operation as it is here, P or R. So this is distribution. The same thing applies to the AND operation also. Yes, the same thing is for the AND operation also. P and Q or R, first combining the AND operation among P and Q, or next Q, P and R. So similarly, one needs to understand, or one needs to keep in mind these few uh, equations also. I can say between P and Q. Negation of P or Q is equal to negation of P and negation Q. Okay, negation of P and Q, something like what you have seen in the De Morgan's in the same manner. And this is most important one. P conditional Q is equal to, we can, P conditional Q is similar to writing it as negation of negation of P or Q, or sometimes you even need to write P and negation of Q by closing enclosing the brackets among P and negation Q, and or else you can directly write as negation of P or. So this is something which needs to be kept in mind while solving some equations, and which helps you in proving some equations or proving certain theorems, and solving many problems. And transitive property, the transitive property states that for all real numbers x, y, z, if x is equal to y and y is equal to z, then x is will be equal to z. Substitution, if x is equal to y, then x may be replaced by y in any equation or in a expression. So till here we have just seen the laws and some of the equations, and which can even be proved also by using the truth table. Let's not prove by using a truth table, and let's keep it in mind, and we'll solve some of the problems. Okay, thank you.